In this video, we'll look at pump and pipe sizing best practices using a systems design approach. A systems design approach means looking at the entire hydraulic system as one connected network, not sizing each component in isolation. That's important because the pump, pipework, fittings, valves, elevation changes, heat transfer, and fluid properties all interact. Change one part, and you affect the flow rate, pump duty, pressure losses, temperature profile, and even whether the fluid stays safely in the liquid phase. Spreadsheets and hand calculations are useful for early estimates, but they treat components separately. That can leave you with a design that looks fine on paper but doesn't perform as expected when the full system is considered. In this example, the model is already set up in FluidFlow, and we'll use it to walk through a liquid transfer system for molten naphthalene. Naphthalene is pumped from a supply tank to a reaction vessel. The tank holds molten naphthalene at around 90 degrees Celsius with a base elevation of 1.0 meter and a liquid level of 1.2 meters. The pump sits at 0 meters and the reaction vessel at 4 meters. The pipework runs at least 200 meters and includes a feed heater, several bends, a check valve, and full-bore ball valves. The design flow rate is 80 cubic meters per hour, set by the reactor's production requirement. The feed heater raises the naphthalene from roughly 90 degrees Celsius to 105 degrees Celsius before it reaches the reactor. That temperature rise isn't just a process requirement, it's also critical for reliable operation. Naphthalene solidifies below approximately 80 degrees Celsius, leaving only a narrow margin. That means heat loss, insulation, startup, and shutdown all play a much bigger role than in a typical transfer system. For any pump system, start by defining the required flow rate, here 80 cubic meters per hour. Next, determine the total differential head needed to deliver that flow. This depends on elevation, friction losses, fittings, valves, equipment, and the fluid properties at operating temperature. That's why you can't size a pump without considering the pipework. A pump operates wherever its performance curve intersects the system curve. If the system curve is wrong, the pump won't operate at its intended duty point, best efficiency point, or even within its safe operating range. A good starting point is sizing the pipework using economic criteria, balancing installation cost, operating cost, energy consumption, and maintenance. Then decide how you'll control the flow rate with a control valve or a variable speed drive. In this example, we'll use a variable speed pump because it reaches the duty point directly instead of wasting excess pressure through throttling. Once the design flow rate is set, FluidFlow can evaluate the system losses and help size the pipework. To automatically size the pipes, FluidFlow offers several options, including economic velocity, design velocity, and design pressure gradient. Here, we'll choose economic velocity to develop the most economical design. The model returns an economic velocity of 1.27 meters per second at the heater inlet and 1.30 meters per second at the outlet, giving economic pipe sizes of 149.1 and 148.2 millimeters respectively. Because the values are nearly identical, we'll use the longer pipe section at the heater outlet. The existing pipe is 6-inch Schedule 40 with an internal diameter of 154.1 millimeters, giving a velocity of 1.21 meters per second, well within the economic range, so we'll keep it. Reducing it to the next standard size, 4-inch, increases the velocity to 2.74 meters per second, but velocity is only one consideration. We also need to weigh pressure loss, pump duty, operating cost, future capacity, and fluid-specific risks. For molten naphthalene, thermal behavior matters just as much as hydraulics. A larger pipe reduces friction loss but increases surface area and fluid inventory, leading to greater heat loss and a higher risk of cooling during low flow or stagnant conditions. A smaller pipe does the opposite. The best choice balances hydraulic performance, efficiency, cost, and reliable thermal operation. We'll proceed with the 6-inch, 154.1 millimeters pipe. Next, calculate the total system loss to determine the pump duty required to deliver 80 cubic meters per hour through the complete system, including the heater, fittings, valves, and elevation changes. The static head comes from the elevation difference, while the tank's liquid level above the pump contributes to the suction side static head. Running the calculation, the model gives a duty pressure rise of 12.36 meters of fluid and an NPSH available of 12.61 meters. These are both system properties. They don't depend on the pump. What we can't determine yet are pump-dependent values such as efficiency, power, and NPSH required. For those, we need to select a candidate pump. Before sending the duty to a pump supplier, confirm the essentials. The supplier reviews the duty point, fluid properties, temperature, viscosity, vapor pressure, materials, sealing arrangement, and NPSH requirements to confirm the pump is suitable for molten naphthalene service and operates near its best efficiency point. On the process side, also decide whether insulation alone is sufficient, or if heat tracing, drain points, warm-up procedures, or thermal expansion relief are required where liquid could become trapped between isolation valves. With a candidate pump assigned, in this case pump sizing demo, solve the model and the pump-dependent results become available. Duty flow, pressure rise, efficiency, power, and NPSH available versus required. This NPSH comparison is one we couldn't make earlier. NPSH available is a system property, while NPSH required comes from the pump. For hot liquids, this check is especially important because vapor pressure increases with temperature. At its base speed of 2,900 RPM, the pump delivers 93.2 cubic meters per hour, exceeding the 80 cubic meters per hour target, at a pressure rise of 16.01 meters. Efficiency is 81.4%, power is 4.8 kilowatts, and NPSH available comfortably exceeds the required value, 12.59 meters versus 7.62 meters, so cavitation isn't a concern. The only issue is that the pump delivers more flow than required. Since we're using a variable speed pump, we simply reduce the speed. Lowering it to 2,536 RPM brings the flow to 80.0 cubic meters per hour with a pressure rise of 12.37 meters, matching the system requirement. Efficiency remains high at 81.47%, power drops to 3.2 kilowatts, and NPSH available still comfortably exceeds NPSH required, 12.61 meters versus 5.65 meters. FluidFlow automatically applies the pump affinity laws when the speed changes, so the related warning message is expected. The hydraulic design now meets the required duty, but before moving on, let's see what happens if we oversize the pipework. It's common to increase pipe size for future capacity or simply to add a safety margin. Let's see what happens. We'll increase the pipe from 6-inch Schedule 40 to 10-inch Schedule 40 and recalculate the model. Immediately, two warnings appear. The duty flow now exceeds the pump's maximum recommended flow, and NPSH available is no longer sufficient. The pump curves explain why. The larger pipe has much lower friction, so the system curve flattens and the duty point shifts to the far right of the pump curve. Flow increases to 114.1 cubic meters per hour at a pressure rise of just 8.22 meters, far more flow than required at a much lower head. That shift creates two problems. NPSH available is 12.67 meters, now below the required 12.92 meters, placing the pump in cavitation territory. At the same time, efficiency falls to 60.91%, moving the pump well away from its best efficiency point. The lesson is that bigger isn't always better. Lower friction pushes the operating point to higher flow, where NPSH required increases and efficiency drops. For molten naphthalene, the impact goes beyond hydraulics. A larger pipe also holds more fluid and has more surface area, increasing heat loss and the risk of solidification during low flow or stagnant conditions. Oversizing compromises both pump performance and thermal performance. Undersizing isn't the answer either. It increases pressure loss, pump head, and energy consumption. The goal is balance. Pipe size and pump performance must be considered together. We'll return to the economic pipe size before moving on. For molten naphthalene, hydraulic performance is only half the design. The thermal design is just as important. The feed heater raises the fluid to 105 degrees Celsius, giving a margin above the 80 degrees Celsius solidification point. But that margin is relatively small. If too much heat is lost downstream, the naphthalene can begin approaching its solidification temperature before reaching the reactor. That's why the model evaluates heat loss as well as pressure loss. It considers pipe length, diameter, ambient temperature, wind speed, emissivity, and insulation. Across 200 meters of pipework, heat loss can become significant. As the fluid cools, viscosity increases, pressure losses rise, and the risk of partial solidification or blockage grows, particularly during startup, shutdown, or low-flow operation when the fluid remains in the pipe longer. Let's evaluate how insulation affects the system's thermal performance. Let's look at the numbers. The heater's 15 degrees Celsius temperature rise adds roughly 528 kilowatts to the fluid. Across the uninsulated pipework, however, more than 155 kilowatts are lost, and the naphthalene reaches the reactor at only 98 degrees Celsius. Much of the available thermal margin has already been lost. Adding 25 millimeters of mineral wool reduces heat loss from 155 kilowatts to 16.27 kilowatts over the 200-meter run. Increasing the insulation to 50 millimeters reduces it further to around 10 kilowatts, allowing the naphthalene to arrive at the reactor at approximately 105 degrees Celsius, essentially maintaining the heater outlet temperature. This demonstrates how effective insulation can be. With only about a 25 degrees Celsius margin above the solidification point, losing 7 degrees Celsius in bare pipework is significant. And steady-state operation isn't the only consideration. Startup before the line is warm, shutdown with fluid remaining in the pipe, draining, heat tracing, and low points where solids can collect all affect whether the system operates reliably. For molten service, these aren't secondary considerations, they're fundamental to the design. The final design should be reviewed from both hydraulic and thermal perspectives. Hydraulically, the system should deliver 80 cubic meters per hour at the required duty while maintaining acceptable velocity, pressure loss, efficiency, and NPSH margin. Thermally, the naphthalene must reach the reactor at the required process temperature while remaining safely above its solidification temperature throughout the transfer. That requires appropriate insulation or heat tracing, depending on operating conditions. This case study highlights why pump and pipe sizing should never be treated as a series of isolated calculations. Pipe size influences pump performance, pump selection affects operating efficiency and NPSH, and thermal losses can determine whether the process remains operable. A systems design approach brings these factors together, allowing you to optimize the hydraulic and thermal performance of the entire system, not just its individual components. For molten naphthalene, maintaining temperature is just as important as delivering flow. The heater raises the fluid to 105 degrees Celsius, but the system must preserve that temperature all the way to the reactor. That's the value of a systems design approach, evaluating the system as a whole to deliver a design that's both efficient and reliable.